Imagine a future when nothing in healthcare is left to chance. Every drug, every procedure, every possible complication is tested first. Not on the patient, but on a virtual copy that mirrors them down to the tiniest detail. Surgical outcomes are tested, and patients get to see their health right in front of them and make informed decisions. This isn't science fiction, but a future we're stepping into. And before we take a look at this technology, let's go back in time. In 2002, Dr. Michael Greaves introduced a bold, futuristic concept at the University of Michigan, a new way to think about how products are built, managed, and evolved. He called it the mirrored spaces model. The idea was massive in potential. There would be three components: a real physical product, its virtual counterpart, and the connection, a continuous flow of data between the two spaces. Together, this model could simulate, monitor, and predict the product's performance in real time without ever needing to touch the real thing. And by 2006, Dr. Greaves refined the idea even further. He realized that the link, the data, was the most powerful piece, and also introduced the possibility of multiple virtual models, each analyzing a different aspect of the same product. And this evolution was called the information mirroring model. But here's the thing, it was way ahead of its time. With the computational infrastructure of the 2000s, this idea seemed like science fiction. And fast forward to 2010, the concept had evolved far enough to appear in one of the world's most advanced organizations, NASA. The term digital twin was used for the first time in their official roadmap, and one of their papers described the use of digital twins for real-time spacecraft health monitoring, material design, and mission planning. Another paper by Dr. Greaves and NASA's principal technologist defined digital twins as: a digital twin fully describes the potential or actual physically manufactured product, from the microatomic level to the macrogeometrical level. Any information that could be obtained from the physical product can also be obtained from its digital twin. And NASA had already used this concept in practice over 40 years ago. In 1970, during the Apollo 13 mission, disaster struck when an explosion tore through one of the spacecraft's oxygen tank, crippling its power and leaking vital resources into space. The team needed a way to return to Earth safely, and they were mid-flight towards the moon. There was no room for error and no margin for risk. Back on Earth, NASA's ground team returned to simulators, recreating the exact conditions of the damaged spacecraft. They tested every possible scenario, every possible fix, for every problem the spacecraft faced in space, until they got the best solution. And against all odds, they brought the crew back home alive. That's the difference. A digital twin is not just a variation of a simulation. It's adaptive, dynamic, and communicates two-way. And with NASA's 2010 adoption of digital twins in their production and testing, other aerospace industries like Lockheed Martin started exploring them. And the popularity rose when more publications were made. With the rise of computing power driven by Moore's law, which predicted that the number of transistors on a chip would double roughly every 2 years, simulating prototypes and running virtual tests became far more efficient and cost-effective than building physical models. Imagine bringing a product to life entirely in the digital world. Every stage, design, testing, and optimization can be explored virtually. Countless what-if scenarios can be run without ever building a single physical unit. Industries caught on to this idea and started making progress. But it wasn't until 2020. COVID-19 brought the world to a standstill, and everything had to find a way to move forward without physical interaction. For industries, this posed a critical challenge: to monitor and optimize complex workflows, test different conditions, and maintain supply chains without being physically present. It wasn't enough to rely on basic simulations. They needed a precise, real-time digital reflection of the real-world systems.
It became clear that the ability to operate, test, and troubleshoot remotely wasn't just an advantage, it was essential. And that's when digital twins began to evolve and multiple industries began to adopt it. From product designing, remote monitoring, autonomous device testing, and even urban planning.
As computational power caught up, digital twins went from bolts and nuts to a whole country. That's not an exaggeration. Singapore became the first country to build a full digital twin with real time monitoring of traffic, resources, and even populational growth.
But here's the catch, everything humans have created is synthetic. Machines, factories, supply chains, they all follow rules we designed, and that makes them easier to replicate in a virtual world. But as humans, we're still trying to understand what makes us who we are, and trying to build an exact digital twin of a human being, that's something else entirely. It's not just complex, it's beyond challenging.
In 2019, a team at the University of Ottawa developed the first digital twin of the human heart, called the cardio twin. It took real time data from peripheral sensors, mobile phones, and social network of the patients, and with the help of a convolutional neural network model, it predicted the probability of an ischemic heart disease even before the patient experienced it.
It was more of a refined cardiovascular AI model than actually a digital twin, one you can think of as a super intelligent cardiologist on the cloud. It was a giant leap forward, but it just scratched the surface.
Over in Barcelona, things were speeding up. Within one of the most powerful supercomputers, the Mare Nostrum, lives something extraordinary. A virtual replica of a human heart made up of over 100 million patches of simulated cells that is still pumping inside a living person. And as it beats, it silently tests treatments from medications to surgical implants without ever touching the body. And across the Atlantic was another breakthrough.
At Johns Hopkins University, scientists took a different approach.
They digitally recreated the upper chambers of the heart to precisely guide doctors in treating irregular heart rhythms.
This wasn't just an academic exercise, it was the first digital twin to be approved by the US FDA. And even more, it was the first digital twin to be ever used in a randomized clinical trial.
Today, we are seeing not just one but multiple digital models of the human heart, and even virtual twins of other organs taking shape.
But here's the important part, healthcare digital twinning isn't just about replicating anatomy, it's about capturing the entire system, the interaction between patients, clinicians, devices, and data, all working together to improve the outcome.
And with the rise of workflow platforms like OpenUSD and Omniverse, we are now able to do something once unimaginable. Entire operating rooms can be virtually recreated, allowing surgical teams to step into near real simulations where they explore every what if scenarios before ever stepping into the real OR. Train surgical robots in virtual space and predict surgical outcomes on models similar to the patient's.
This is promising, but the deeper we go, the more complex it gets. To build digital twins at this level of complexity and scale, we still face some serious roadblocks. We need more than just advanced models, we need data. Data that flows seamlessly across precise, reliable sensors embedded across the system. And not just any data, but standardized, high fidelity information that can be trusted without question. Sensors that communicate in real time, integrating effortlessly with other systems to enable a fully connected healthcare ecosystem, both physically and virtually, so that every risk can be explored in the virtual world and only the best, safest decisions can be brought to the real world. Because in medicine, even the slightest variation, a fraction of a degree and a delayed signal, could be the difference between life and death. If we are going to use technology to guide care, then that technology must be precise. This future might seem close to impossible, but it's not impossible.